So in the following videos, we are gonna compute representation numbers for quadratic spaces over a finite field. So let's say V is a regular quadratic space over a finite field F with quadratic form Q. Let's say F is the finite field F little q. That's why we use this notation for the quadratic form so that they are different. So what's the representation number of some alpha in F? That's just the number of vectors x in V that represents alpha. So the value of the quadratic form at x is equal to alpha. We want to give an explicit formula for this in terms of the dimension of V. To that end, first we want to discuss a lemma to bring the computation of such numbers back to the computation of representation number of just 0, just the case when alpha is 0. We will first compute this for even dimension. So let's say V has even dimension 2k, and let alpha be any non-zero element of F. Then we claim that the number of representations of alpha is as follows. We can write it in terms of the number of representations of 0 as follows. Note that this implies that the number of representations of any element, non-zero element in F are the same. What we mean is that if we can show that the number of representations of any non-zero elements of F are the same, like this, then we can deduce this equality. And why is that? Well, so every element of V either represents 0 or represents some non-zero element. How many elements does V have? Well, V is of dimension 2 to the 2k, so we have 2 to the k vectors. Now F star has how many elements? Q minus 1, right? So if the number of representations of each of these elements are the same, then it will each be equal to this total number of vectors in V minus the ones that represent 0 and then divided by q minus 1. So it suffices now to show that the number of representation of any non-zero element is going to be equal to the number of representation of 1. The key idea is that both are gonna be equal to the number of representation of alpha but under a different form, right? Under the form Q alpha, which we will explain. So given the alpha that is non-zero, we can consider the following space, which is called a scale space of V. As a vector space is equal to V, but the bilinear form on it is different. The bilinear form on it is gonna be alpha multiplied with B. So that if A is the ground matrix of V, then alpha A is the ground matrix of this scale space. Thus we see that if V, then a little v represents 1 in big V, if and only if it represents alpha in the scale space, right? So the number of representations of 1 in V is equal to the number of representation of alpha in the scale space. Now what we want to show is that the number of representation of alpha in the scale space must be equal to the number of representation of alpha in V. And to that end, it suffices to just show that V and the scale space, they are isometric. But these are vector spaces, quadratic spaces over a finite field, and we know how to classify all such spaces. We know, so it's by dimension and discriminant. These spaces have the same dimension, so the only thing we need to check is that they have the same discriminant. Now what are their discriminant? Well, the discriminant of V is just the determinant of A. The discriminant of V alpha is the determinant of alpha A, and no, that's not equal to alpha times the determinant of A. Remember, that should be alpha to 2 to the k times the determinant of A. And here's where we use the hypothesis that V is of even dimension, because then these are going to be equal modulo a square, because the discriminant is only determined up to a square. So the discriminant of these are the same, their dimension are the same, so these two spaces are isometric, and thus the number of representation of alpha in V alpha is equal to the number of representation of alpha in V. And so that means that the number of representation of alpha in V must be equal to the number of representation of 1 in V. So the number of representation of all of the non-zero element in V are the same. And thus we get the following formula.